The next thing that we are going to talk about vectors is the dot product. The dot product of two vectors. So let's define what the dot product is. This is used both in R2, meaning that the vectors have two coordinates, or in R3, that the vectors have three coordinates. Let me define both cases. Like in R2, suppose I have two vectors. So let U vector U be A1, A2. And vector V, suppose it is B1, B2. The dot product of these two vectors, so U dot V. The dot product of a vector is a number. That number is computed in this way, or is defined in this way. The first coordinate of U, which is A1, times the first coordinate of V, which is B1, plus the second coordinate of U times the second coordinate of V. So that's how the dot product in R2 is defined. In R3, so this is in R2. In R3, we define the dot product in a similar way. So in R3, let vector U consists of three components, A1, A2, A3. And vector V consists of also three components, B1, B2, and B3. Then U dot V is defined as first coordinate of U times first coordinate of V, so A1, B1, plus second coordinate of U times second coordinate of V, plus third coordinate of U times the third coordinate of V. So let's see some examples to clarify this. Example, compute these dot products. The first part, suppose I want to compute the vector 2, 3 dot vector 5, 1. Again, as usual, try to do this on your own before watching the solution. So the first coordinate times the first coordinate, 2 times 5, regular multiplication, plus 3 times 1. So they add up to 13. So as you see, the dot product of two vectors is a number. Let's see another example. Part 2. In the next example, let me, instead of using this notation, use the other notation of with I and J. Suppose I have 4I plus 3J, this vector, dot product by the vector 6i minus 10j. So similar situation, the first coordinate of the vector u, which is 4, is multiplied by 6, so 4 times 6, plus the second coordinate of u times the second coordinate of v, 3 times negative 10. And they add up to negative 6. So the dot product of these two vectors is negative 6. Just as a clarification, this example could have been given using the other notation. So this would have been 4, 3. And the other vector would have been 6, negative 10. But regardless of which notation that you use, we should get the same answer. Let me do an example in R3. Suppose I have 1, 1, 5. Dot product by the vector 2, negative 3, and 0. Again, the outcome is a number. First coordinate times first coordinate, 1 times 2, plus 1 times negative 3, plus 5 times 0. So the final answer, which is just a number, is negative 1. So the dot product of these two vectors is just negative 1. Also, let me give an example in R3 that instead of this notation, we use IJK notation. The first vector is minus 2i plus 3j minus k. Usually I put an arrow on IJK to emphasize our vectors, but now we have worked with this in the last 2 or 3 videos, so we are we know that IJK and which vectors they are. So I don't need to really put an arrow up above them. So dot product 5i plus 4j minus 3k. Again, you can pause the video, try to do this on your own, and check the answer to see that you get the same value. At the end, we should get a value, a number. The outcome of a dot product is a number, is not a vector. So minus 2 times 5 plus 3 times 4 plus, so that minus k means minus 1 times k. So this is minus 1, minus 3k is like, and minus 3. Just for clarification, I could have looked at this as the vector -2, comma 3, comma -1, and the other vector as 5, comma 4, comma -3. So now if you calculate this, you should, as you probably have obtained the value at the end is going to be equal to 5. Okay, let me do another example. Again, please try this on your own before watching the solution. Suppose the first vector, again, I show both of the vectors in I, j, k. Suppose the first vector is I plus 5j plus k, and the other, so dot product by -3i plus 6k. Please pay attention that in the second vector, we don't see j, which means the coefficient of j is 0. So if I want to use the other notation, this means the vector, the first vector is 1, comma 5, comma 1. The second vector, coefficient of I is -3. So the first coordinate is -3. I don't see j, which means it is 0j. So the second coordinate is 0, and the coefficient of k is 6, means that the third coefficient is 6. So when I do the product here, we should pay attention to the point that since in the second vector we don't see j, it means that the coefficient of j is 0. Okay, so if I do the dot product, the first coordinate times the first coordinate, 1 times -3. I add up to the product of the second coordinates, 5 times 0, and add up to the product of the third coordinates, 1 times 6. Obviously, these numbers add up to 3. Okay, in this regard, there is another way to obtain the dot product. And the other way that I state this as a formula here is like let u and v be two vectors, and theta is the angle between these two vectors. Then there's another way, as I said, as a formula that we can compute the dot product. U dot v equals length of u times length of v times cosine of theta. This could be in R2, in R, or in R3. So if I have two vectors, suppose, say this is U, it could be in two-dimensional space or three-dimensional space. And suppose this is V, So this is vector u and vector v. And the angle, they make an angle of theta. Then u dot v is computed this way. In some texts, they take this as the definition of, like in R2, the first one, in R3, the second one, as the definition of the dot product. Then this can be proved as a theorem that the dot product can also be computed this way. In some other texts, they go the other way. They take this as a definition, then they prove the initial definition that we made for the dot product. So if we assume one of them as a definition, the other one can be proved. But in any way, it turns out these two definitions are equivalent, meaning that they result in the same value for the dot product. One of the good things about having these two definitions is, one of the applications is, we can compute the angle between two vectors. So let's see an example that by setting these two ways of defining the dot product equal to each other. As I mentioned, it can be proved that they are the same, that the two definitions are equivalent. I can find the angle between two vectors. Let's see an example. In this example, I want to find the angle theta between the two vectors. One of them 1, 3, and the other one is -5, 1. I want to see that what angle these two vectors they make. So one way to the very first definition that we had in this video, the dot product of these two. Let's compute that to see what value we get. So this is going to be 1 times -5 plus 3 times 1, which results in -2. This dot product was calculated by using the very first definition that we had here on the top in R2. If U has 2 coordinates, V has 2 coordinates. That's how the dot product is defined. But let me use the other way of obtaining the dot product this way. So here, the dot product of these two vectors is the length of the first one times the length of the second vector times cosine of the angle they make. So now what is the length of 1, 3? As you might remember, it is radical of 1 squared plus 3 squared, which is radical 10. The length of this vector is radical of -5 squared plus 1 squared, which is 26 under the radical. Now I set these two values equal to each other because they are the same thing but obtained using two different formulas. So radical 10 times radical 26 times cosine of theta is -2. I want to find the angle between the two vectors. If I first of all, radical 10 times radical 26 is radical 260. At this point, we don't need to simplify. So I get cosine theta is -2 over radical 260. As you have seen in pre-calculus, for finding theta, we can use cos inverse or arc cosine. So theta angle is cos inverse of this fraction. As you know, on your calculator, there is a cos inverse button, which is, in fact, the second function of cos. On the button that has cos, as you know from pre-calculus, the second function is cos inverse. Suppose at the end, I want to show my answer in terms of degrees. Let me put a degree sign over here. So I want to show my answer in degrees. And I have this explanation round to 1 decimal place. And you should round this at the end of your solution, not in the middle of your solution. So you, on your calculator, use cos inverse and then type -2 divided by radical 260. And make sure that since in this example, we want to find the degree in terms of, we want to find the angle in terms of degrees, set your calculator on the degree mode, not radians, because here, this sign here is the sign of degrees. So we need to set the calculator on the degree mode. This is something that you have done in pre-calculus. And if you do it correctly, at the end, you should get the angle is going to be 97, rounded to 1 decimal place, 97.1 degrees. So based on this example, let me write a note. And I will have a similar note for the three-dimensional space. So let A1, A2, and B1, B2, B2 vectors in R2. Then the angle theta between the two vectors can be calculated by this formula. Theta is cos inverse of A1 B1 plus A2 B2 divided by the length of the first vector, which is radical of A1 squared plus A2 squared, time in the denominator, time the length of the other vector B1 squared plus B2 squared. So this is the formula that we use to find the angle between two vectors in R2. Again, the reason that that is correct is because in one way, I obtained the dot product of the two vectors by A1, B1 plus A2, B2. In the other way, I obtained the dot product by the length of the first vector times the length of the second vector times cosine of theta. I solve for cosine, and then I apply the cos inverse. That's exactly what we did in the previous example. As I mentioned, the same similar formula can be used for 3-dimension. So let me talk about that as well. So let's A1, A2, A3. Now we have three coordinates because we are in R3. And B1, B2, B3, B2 vectors in R3. Then the angle theta between the two vectors can be calculated by this formula. Theta is cos inverse of what? Of, on the top, I will have A1 B1 plus A2 B2 plus A3 B3. At the bottom, I will have length of the first vector, which is A1 squared plus A2 squared plus A3 squared times the length of the other vector, B1 squared plus B2 squared plus B3 squared. Again, let me explain why this formula is valid. So the explanation of this will be on the next slide. The reason is I obtained the dot product in two different ways. One way is the very first slide of this video that we define dot product by this calculation A1 B1 plus A2 B2 plus A3 B3. The other way that we can obtain the dot product is dot product of the same two vectors. The length of the first one, which is radical of A1 squared plus A2 squared plus A3 squared times the length of the second vector, B1 squared plus B2 squared plus B3 squared times cosine of theta. Theta is the angle these two make. So I set these two equal to each other. They are the same thing obtained in two different ways. So that radical A1 squared plus A2 squared plus A3 squared times the radical of B1 squared plus B2 squared plus B3 squared times cosine of theta is A1 B1 plus A2 B2 plus A3 B3. So I solve for cosine, meaning that I divide both sides by this product. So what I get is cosine of theta is A1 B1 plus A2 B2 plus A3 B3 divided by the product of those radicals, A1 radical of A1 squared plus A2 squared plus A3 squared times radical of B1 squared plus B2 squared plus B3 squared. And from here, I get to the formula that you see on the previous page, that theta is cos inverse of this ratio A1 B1 plus A2 B2 plus A3 B3 divided by radical of A1 squared plus A2 squared plus A3 squared times the radical of B1 squared plus B2 squared plus B3 squared. Again, for clarification, this page is just why the formula is valid. The formula that we just discussed here. This is the explanation that why the formula is valid. I obtained the dot product in two different ways, set them equal to each other, and calculated theta. Okay, let's see an example for the case of R3 that we find the angle between the two vectors. So let these two be the vectors that we want to find the angle. Let 3 minus 2 minus 1 and 1 1 0 be two vectors. Find the angle between them. So find the angle between the two vectors. Suppose at the end, I want the angle here and in terms of degrees and round to 1 decimal place. Again, please try this on your own before looking at the solution. So using the formula, we have theta is cos inverse. So I obtained the dot product in the way that we initially defined. 3 times 1, the first coordinate times the first coordinate, plus -2 times 1, second coordinate times second coordinate, and finally plus -1 times 0. In the denominator, we use the length of these two vectors, radical of 3 squared plus -2 squared plus -1 squared. This is the length of the first vector, this vector here. The length of that is radical of 3 squared times -2 squared. I'm sorry, 3 squared plus -2 squared plus -1 squared. And times the radical, which is the length of the other vector. So 1 squared plus 1 squared plus 0 squared. So in fact, I should calculate cos inverse of, on the numerator, 3 times 1 plus -2 times 1 plus 0 gives me just 1. The first radical is radical 14. Second radical is radical 2. The product of these two is radical 28. At this point, we don't need to simplify anything. We don't need to round anything. We do the rounding at the end of the solution. If I round like radical 28 at this step, I might get a wrong answer because it increases the error. And if you calculate this and round it to 1 decimal place, you should get 79.1 degrees. Again, make sure that your calculator is set on the degree mode. Another example, again, find the angle. Between these two vectors, I plus 2j plus 3k and minus I plus k. Again, please pause the video and try to do this on your own. If you're more comfortable with the other notation, you can use the other notation. 1, 2, 3 is the first vector. And the other vector, -1. I don't see j, which means it is 0 and 1. So again, theta is cos inverse. First number times first number, 1 times -1. Second number times second number. There was no need to parentheses. And plus just parentheses here. 3 times 1. At the bottom, the length of this vector 1, 2, 3, which is radical of 1 squared plus 2 squared plus 3 squared. And the radical of, in fact, it's the length of the other one, the radical of minus 1 squared plus 0 squared plus 1 squared. So we have cos inverse. And at the end, suppose I should have mentioned this before. I want to answer in degrees and again, rounded to 1 decimal place, round to 1 decimal place. On the top, I have 2. At the bottom, the first radical is radical 40. The second radical is radical 2, so radical 28. If you calculate this and round to 1 decimal place, at the end, you should get 67.8 degrees, round to 1 decimal place.